Hey, how's it going? Before we jump into the content, I just want to take a minute to thank you for stopping by the channel and checking out the content. If you like this content and you want to support more content like it, then make sure to subscribe to the channel and like this video. You can also check out the YouTube membership program and cybertrainingpro.com, where I put practice exams and other things that I couldn't put on YouTube. Again, regardless of how you support the channel and my content, I couldn't be more appreciative. Thank you so much, and let's get into the content. We've talked a lot in this course about the OSI model and how it helps people and technologies speak the same language. The reason is, of course, that when networking was first starting to evolve in the 1980s, every company was trying to create their own protocols, but unfortunately, nobody had a protocol that could do everything that a network needed. The TCP/IP protocol suite was the one that was developed in order to standardize some of this stuff, and it's what you need to know about. If you refer back to the OSI model, the TCP/IP protocol operates at layers 3 through 7. All right, let's begin. Remember when we talked about IP addresses? Well, IP, or the Internet Protocol, works at the network layer, where it takes chunks of data from the transport layer and it creates packets to hand it to the data link layer to pack it into a frame. Now, most people have seen an IP address that uses an Internet Protocol version 4, like 192.168.1.20, where each value can range from 0 to 255. Of course, in the future, IPv4 is going to be replaced by IPv6 just because we have so many devices that are starting to be connected to the internet. The Internet Control Message Protocol, or ICMP, also works at the network layer. Users don't typically use this protocol directly, though, unless they want to ping a system to make sure that it's alive. As you can see on the screen here, I've included a full diagram and a simplified diagram of an IPv4 header. But let's go ahead and focus on that simplified version, which actually has a lot more fields, but there's a few that we need to focus on for right now. Version, which will indicate either IPv4 or IPv6. Total length, which is the size of the IP packet and has a field length of 16 bits and a packet size limit of 65 kilobits. Time to live, or TTL, helps preventing loops and decrements by 1 every time the packet goes through a router. A lot of times Linux systems will start at 64 and start counting down, and Windows systems will start at 128 and they'll start counting down, but numbers can't start higher than 255. And protocol, which is usually going to either be TCP or UDP. Whenever data is being transported to different systems, the systems need to know whether they need to verify and make sure the data gets there successfully, which will use TCP, or if they can just get the data and forget, which is going to be UDP. We as the users don't actually select TCP or UDP, but whoever develops an application is going to make that decision. TCP stands for Transmission Control Protocol, and it's the most commonly used of the two options. One of the key things to remember when it comes to TCP is something called the TCP three-way handshake, which is the process of how systems actually form that reliable connection with each other. We also refer to TCP as a connection-oriented protocol. Now, the TCP three-way handshake works like this. It starts out by a client system sending a SYN packet to a server. Then the server replies with a SYN acknowledgement, or SYN ACK packet, letting that client know that it's ready. And then the client returns an ACK packet, an acknowledgement packet, which finalizes and forms that connection. TCP breaks data into segments. It gives each segment a sequence number, and then it verifies that all packets are received. Now, if a segment is missing, that system actually can request a new copy of those missing segments. You can see what a simplified TCP header looks like on the screen here. Now, the source port is used to remember who sent the data. Again, sequence number and acknowledgement number help with keeping track of received data and if there's any missing data. You might see TCP flags, which give each side of the connection information about the state of that connection. Checksums might also be used by the receiver to check the TCP header for errors, like bits flipped, or if they're lost during transmission. UDP, or User Data Protocol, is often referred to as a fire and forget protocol because once it sends data, it forgets about it completely. UDP also doesn't need some of the extra fields like we see in TCP because it doesn't care about a lot of that stuff, and that actually makes it really fast too. Also, UDP datagrams don't get broken into segments. They just get a header and they get sent. Now, a few common protocols that use UDP are Domain Name Service, or DNS, and Dynamic Host Configuration Protocol, or DHCP. You can see a simplified version of a UDP header here on the screen. One of the most common examples of the application layer in action can be seen when you actually look at an HTTP header. TCP/IP enables us to create small connected networks called LANs, or local area networks. We can also connect those smaller networks together in a WAN, or a wide area network. Typically, when we talk about a LAN, we're referring to a small area, like a single building. But when we talk about a WAN, we're talking about a wider geographic area. For example, the United States. We might have a WAN that connects Miami, Florida with Los Angeles, California. If you aren't familiar with how local area networks operate, I highly recommend checking out the videos on the OSI model layers so that you can have a better understanding. Typically, with local area networks, communication happens using Ethernet frames and MAC addresses. So what happens if the sending computer doesn't know the MAC address of the receiver? It sends out an ARP request or an address resolution protocol request to the broadcast address of FF, 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 FF. So that's 6 groups of 2 Fs with the receiver's IP address, which gets sent to all the ports on a switch. The receiver then replies with the MAC address. If you want to see the MAC address that your system knows about, open up a command prompt or terminal window on Linux and type ARP-A. You can also delete an entry by typing ARP-D and then the IP address. If you ping a deleted host, what happens when you type ARP-A again? IP addresses are also important when it comes to networking, and no two systems are going to have the same IP address, just like with MAC addresses. Most commonly today, we use IPv4 addresses, which are 32-bit values that we write in decimal notation of 8 bits each, with values from 0 to 255. But we can also write them in binary, like we have on the screen here. Being able to convert between decimal and binary is a very useful skill, but in the real world, you're actually going to use a calculator or a converter to speed up that process. If you want to see your IP address, open up a command prompt in Windows and type ipconfig, or if you're on Linux or Mac, you can use ifconfig, or you can use the IP command in a terminal window. Alternatively, most operating systems will have a GUI that you can also see the same information. Now that you know what an IP address, let's talk about how it all works together. There are 3 things that your IP addressing system needs to do. It needs to create network IDs, it needs to connect LANs together using routers so that packets can get where they need to go, and use a subnet mask for each computer so that they know how to handle the packet. We know that WANs or wide area networks connect multiple local area networks together. However, each LAN has some distinguishing factors to identify itself from others. Believe it or not, certain parts of an IP address accomplish just that. If you look at your home network, you probably have an IP address of 192.168.1. something. Well, guess what? The 192.168.1 part of your IP address is your network ID. It's kind of like your street name of your home address. So if, for example, I live at 123 Apple Ridge Lane, then Apple Ridge Lane is my network ID or my street. The remaining part of the IP address is the host ID. For example, your IP address might be 192.168.1.50. This means your network ID is 192.168.1 and your host ID is 50. The host ID in this situation is anything starting at 1 all the way up to 254. Networks with different network IDs have to have a router to connect them. It's just that simple. That's because switches can only transfer data to systems on that same network. Both of the router interfaces or ports that connect each other are called the default gateway, and that will have an IP address and the same network ID as host connected to that port. Typically, the host ID for the default gateway is going to be the number 1. The primary reason for the default gateway is to send traffic destined for other networks. The subnet mask indicates that yes, the network ID and receiving host are either on the same network or a different network. Every subnet mask is exactly 32 bits long, and if you write out the subnet mask in binary, every 1 digit is going to indicate the network portion, and every 0 is going to indicate the host ID. I want you to memorize the chart on the screen because this can be extremely valuable if you have to deal with binary. We use this directly with the subnet mask. So for example, any of the boxes that have a 1 in them will be a value that's added up, and it can be up to 255. That means if you have a 255 in your subnet mask, the binary representation would be 8 ones because each one of these boxes is going to have a 1 in them. The only other option is a 0. So every box is either going to have a 1 or a 0. Converting binary to decimal is pretty easy because if you have this chart filled out with binary, you can just add up all the boxes and their values and see what the value is. If you're converting from decimal to binary, start with the highest number box that is less than the decimal number. So for example, if you had 192 in the subnet mask, then you would start with the 128 box, calculate the difference between the two, and continue the same process until you have 0 remaining. With 192, you would have a 1 in the first box, and in the second box, and then there's a 0 in every other box. You'll do this for each octet or section of the subnet mask. All systems on the same network will have the same subnet mask and network ID. Basically, when a computer is sending out data, it compares the network ID to the destination's network ID, and if they match, then it's local. If the destination isn't local, the sending system is going to send out a broadcast message to determine the MAC address of the default gateway, and then it's going to send the data to it. Let's go through a quick example of how subnetting works. Just so this makes a little bit more sense and you can actually see this, I just want to show you how to do this math. So if you look on the screen here, you'll see a 1 in the 128 box, 1 in the 64 box, and a 1 in the 1 box. So 128 plus 64 is 192, plus 1 is going to be 193. So that would be your decimal value. At first glance here, you might be thinking that the system is trying to send traffic to itself, but I've highlighted the differences between the two. Now, these are two systems on separate networks. They have the same host ID, but they have different network IDs, and the subnet masks are different. I highly encourage you to practice doing this exercise until you feel comfortable doing it without a calculator. Just so you can see it a little bit easier, the binary section is what we were just talking about and how we were writing that out and calculating that out to switch it between decimal and binary. I highly recommend that you practice this a decent amount because it is likely to come up on your exam. When a company like Google sets up their web server, they have a public IP address, which means that traffic can go directly to that IP address across the internet. Public IP addresses are tracked and distributed by an organization called the Internet Assigned Numbers Authority, or IANA. Your internet service providers like Comcast here in the United States get assigned blocks of IP addresses from the various classes on the screen. We refer to this older system, which we don't really use anymore, as classful networks. You can see the math next to the number of hosts can get quite large. The idea with each class is that Class A networks allow you to change the last 3 octets, Class B changes the last 2 octets of an IP address, and Class C can change the last octet of the host IP address. Class D or multicast are messages sent from a single computer to a group of computers, and Class E is experimental, or also called reserved, and is used for experimental purposes. Basically, the classful system was wasteful when it came to distributing IP addresses, so there had to be a better way, called the classless interdomain routing, or CIDR. Classless interdomain routing, or CIDR, was developed to replace classful networks, and it relies on a concept called subnetting. Basically, the idea behind subnetting is that we can take a single class of IP addresses and chop it up into smaller networks called subnets. Now, subnetting has several advantages, including it's more efficient with the use of IP addresses. You can separately transfer traffic for security and better bandwidth control. If you remember about subnet masks, we typically might have a /8, /16, or /24, but we can break it down further if we don't have to use all that space. For example, a /24 network really gives us up to 254 hosts. You can determine the slash number by looking at the binary representation of that subnet mask and adding up all the ones that exist. So in the /8, you can see there's 8 ones, so it's a /8. Make sure that you remember CIDR notation is for classless addressing, also referred to as classless variable length subnet masking, abbreviated as VLSM. Let's do an example using a 192.168.1.0 network with a /24 subnet mask. We're going to change this to a /25 network by the time that we're done. In our /24 network, we can add up all the available IP addresses and subtract 2 for the total amount that we can assign. We do this because the first address will identify the network ID and the last is going to be the broadcast address. Alternatively, we can also count the zeros in binary representation and subtract 2. Now, a quicker way if you're adding the zeros is to do a power of 2 of how many zeros that you have in binary and then subtract 2. Let's somewhat ignore the decimal notation dots for a minute, and for the /25 network, we'll change one of the zeros to a 1. This gives us a 25 for our new CIDR notation. If we go into our chart that we can use for binary and we plot out the binary for /25 networks, what's the number? Remember, we just have to add up all the ones, so it's 128. That means 128 is our answer for /25 networks, so our subnet mask is going to be 255.255.255.128 instead of 255.255.255.0 like it would be for a /24 network. If we were dealing with a /17 network, our new number would be in the 3rd octet, and /9 networks would get the new number in the 2nd octet. You get the idea. The key is that these numbers aren't all or nothing with only either 255 or 0. So how many subnets do we actually get now that we've changed the network to a /25? Well, first of all, we know that we added 1 digit. A simple calculation again, using the powers of 2, we take 2 to the power of 1 in this case, or however many digits that you added, and you get the number of subnets that you can create. In our current example, we can take 256 and divide it by 2, so we get 2 subnets with equal amounts of IP addresses, and we can have up to 126 hosts in each subnet because the answer was 128, but we need a broadcast address and our network ID address. You can see all the related network information that results from the math on the screen. Notice that the subnet mask will be the same for all the subnets. What if you need 3 subnets? Well, we know that there is no power of 2 that will equal 3. We can do a 2 to the power of 1 or 2 to the power of 2, and we get either 2 or 4. So yes, in that particular situation, we would waste a subnet. When it comes to IP addresses, there are 2 ways that they get assigned. Static addressing, which means that you or somebody manually actually assigns a specific IP address, subnet mask, and the default gateway. Or by dynamic addressing, which is where the system is going to automatically assign all that information from a server. When it comes to IP addressing, there aren't a lot of rules with how specific IP addresses get assigned. However, there are a few common practices that we need to use. Default gateways usually get the first or the last IP address of the network ID. Use IP addresses in sequential order, so in numbering order. Separate server IP addresses from clients. So for example, maybe use host IDs of 10 through 30 for servers and 50 and beyond are for clients. Document how you've done everything so whoever comes in after you isn't completely lost. One of the biggest issues with static addressing is that if you have to make any changes, it is a huge pain. You also have to be careful to not assign the same IP address to multiple systems because that's going to cause a problem. Okay, on a Windows computer, if you wanted to configure a static IP address, you could go to the search bar and type in network and network status. Basically, what we're trying to do is we're trying to actually change our network adapter settings. So let's go ahead and click on that. And then you get all these different options here. So we're going to go to the advanced network settings and change adapter options. We'll click on that. And you might have several different network adapters in here, but we're going to right click on this main one, Ethernet 0 for us. Then click properties. And then you're going to select the IPv4 network adapter here. And we're going to hit properties. And then to change this from DHCP to statically configured, you would just have to select this option, use the following IP address, and then you would just fill this in to whatever you wanted it to be. And then you'd fill in the subnet mask to make sure that's correct. It will automatically try to figure this out based on the IP address that you enter in. And then default gateway, you'd want to fill in that for your default gateway, so your router or whatever that is. And then DNS servers, so that way it can resolve DNS information. Now keep in mind, if you do not fill this information out correctly, you might not be able to communicate with other systems. So for instance, if you didn't have this default gateway filled in here, your computer would not know where to send default traffic, which means that you're basically probably not going to be able to connect with the internet and probably not with the rest of your network either. So keep that in mind. And then of course the actual network and subnet mask and all that information really matters too. And if you're on a Linux system, it would be a very similar process where you're changing the IPv4 settings of your adapter. But since there's so many different Linux distributions, we're not going to cover every single one of them because it would be a bunch of different steps. But keep that in mind for whichever distribution that you're using. Dynamic IP addressing uses DHCP or Dynamic Host Configuration Protocol to automatically assign IP addresses to computers that connect to the network. Now, DHCP operates with a server that passes out IP addresses to DHCP clients, which are your computers or other systems. The server can be a network device like a router, or it can literally be a server running an operating system like Microsoft Server with a pool or a range that the DHCP server distributes IP addresses from, and it's called the DHCP scope. An important note here is that since several types of devices have the ability to be a DHCP server, you have to make sure that you disable those DHCP server functionalities on any system that won't be used in that capacity to avoid any kind of conflict. As you can see on the screen here, your router might be a DHCP client with your internet service provider's DHCP server. All right, so this is the DHCP four-way handshake process. It starts out with DHCP clients connecting to the network, and they broadcast a DHCP discover message asking for the DHCP server. Then the DHCP server replies to the DHCP client with a DHCP offer message that includes an IP address, subnet mask, gateway, and other relevant information. DHCP clients then send a DHCP request to make sure that the offer is still valid and to accept the offer. Then the DHCP server sends a DHCP ACK or acknowledgement, and then it lists the client's MAC address as well as the IP information given to the DHCP client in a database. An easy way to remember the process is to remember DORA: discover, offer, request, acknowledgement. After the process is finished, the DHCP server gives the DHCP client a DHCP lease, which says how long that client reserves that information. Usually it's somewhere between 1 and 8 days. Near the end of that lease time, the DHCP client is going to send out another DHCP request message to see if it can get a new lease or if it needs to change the address. DHCP's four-way handshake normally uses broadcast messages to start the process. Unfortunately, routers don't pass on broadcast messages to other networks, but it might not be always practical to have the DHCP server on the same subnet as clients. DHCP Relay enables a router to accept DHCP broadcasts from clients, and then it uses UDP forwarding to actually send them on to unicast addresses directly to the DHCP server. In order for this to work, the router is performing the DHCP relay, and it will need the DHCP server IP address configured as the IP helper address or the UDP helper address. And this is the same thing, but basically it's going to be labeled one of these. We've talked a lot about both static and dynamic addressing, but there are situations where we want to actually assign specific fixed IP addresses, for example, to routers, servers, printers, and cameras. If we gave them dynamic IP addresses, it would be a lot harder to locate them if they ever change. IP reservations prevent these addresses from actually being distributed to systems by DHCP. And there are basically three ways that we can reserve IP addresses. Make the DHCP address pool smaller, so instead of starting at 100 and going to 200, we can make it start at 150. You can use IP exclusion ranges, which allows us to identify ranges within the address pool that shouldn't be distributed, and MAC reservations, which allow us to identify systems by their MAC address that will get a specific IP address. DHCP is an awesome technology that makes life a lot easier. Since we have a high degree of reliance on DHCP, there's some problems that we need to make sure that you're aware of. So no DHCP server. If all of a sudden you can't reach the internet, check your IP address. Does it start with 169? If so, this is a result of zero configuration networking, or zero conf. This is Microsoft's implementation of automatic private IP addressing, or something called a PIPA. If other systems on the same network came up after DHCP went down, they'll be able to communicate with each other, but you won't have a default gateway to reach outside of that network. This is because for this process, the client will only generate the last 2 octets of the IP address. You can try some of the troubleshooting steps to correct this. So I have a lot of the commands on the screen here that I would definitely try if you have this issue. And you can see with Linux, it actually requires you to take the interface down and then bring it back up. With Windows, you can just go in and release and renew your IP address information. Having a single DHCP server can present a single point of failure with DHCP. Ideally, you want to have at least 2 DHCP servers, so that way if one goes down, clients can still get IP addresses. A good idea is to divide the IP address scope evenly between the 2 different servers. This is pretty common in larger networks like enterprise-sized networks. Rogue DHCP servers are unauthorized DHCP servers that pass out incorrect IP information to clients. This can be malicious when an attacker who implements a new DHCP server, or it could be an employee who brings in their own router and that starts passing out information. Malicious attackers implementing a rogue DHCP server are more dangerous than an employee doing this because this can lead to attackers having the traffic route through them, also called a man-in-the-middle attack, and then they can see the actual traffic and do bad things with it. A good way to make it easy to identify these types of servers is to not use default IP address schemes. For example, 192.168.1.0 is the default IP network for a lot of these devices. If you have some people who can access resources and some that can't, you can easily check the IP address, subnet mask, and default gateway to see if they match with what it's supposed to be. That's why documenting information like IP address ranges is extremely important. When TCP/IP was created, there were special IP addresses for specific reasons. The loopback address, or 127.0.0.1, is one that you might have seen before. Anything sent to this IP address is going to be directed to that same system. A random fact is that really that any IP address starting with 127 is reserved for loopback addresses and not just the one that we talked about. There's several reasons to use a loopback address, including to test the network stack of a system. Private IP addresses that are documented in RFC 1918 are addresses that routers will never route directly to the internet. You can see the private IP addresses here on the screen. All other IP addresses are public IP addresses.